Okay, we are at section 19.5, magnetic force on a current carrying conductor. Next slide. Okay. If a magnetic field exerts a force on a single charged particle when it moves through a magnetic field, you might expect that magnetic forces are exerted on a current carrying wire as well, which is indeed the case. This is shown in the photo here because the current is a collection of many charged particles in motion. The resultant force on the wire is due to the sum of the individual forces on the charged particles. The force on the particles is transmitted to the bulk of the wire through collisions with the atoms making up the wire. The figure here demonstrates the force on a current carrying conductor in an external magnetic field. You can see they have a little horseshoe magnet, and when you apply the current, the bar swings toward the magnet after the switch is closed. Okay, let's go to the next. Oops, I lost my place. Here we go. Okay, sorry about that. We can demonstrate the force on a current carrying conductor by hanging a wire between the poles of a magnet as shown in the figure. In this figure, the magnetic field is directed into the page and covers the region within the shaded area. The wire deflects to the right or left when it carries a current. If you look at the figure, when there's no current in the wire remains vertical. When the current is upward, the wire deflects to the left. When the current is downward, the wire deflects to the right. Okay. If you think of the B field into the page, velocity and force, and then we reverse it on the figure C into the page, the velocity downward and the force against this way. You can see it from the right-hand rule. Okay. Now let's quantify our discussion. Consider the figure which shows a straight segment of wire of length L and cross-sectional area A carrying the current I in a uniform external magnetic field B. Let's assume that the magnetic field is perpendicular to the wire and is directed into the screen. A force is exerted on each charge carrier in the wire, where Vd is the drift velocity of the charge. So force is equal to QVB, where the V is the drift velocity. To find the total force on the wire, we multiply the force on one charge carrier by the number of carriers in the segment. Because the volume of the segment is AL, the volume is AL, the number of carriers is NAL. Okay, where N is the number of carriers per unit volume. That means the magnitude of the total magnetic force on the wire of length L is the force on each charge carrier times the total number of carriers. So that's the same thing. Let's see. Okay, force max is equal to QVB times NAL. All right. Recall that the current in the wire is given by the expression shown here, INQV drift times the area, and that's related to F max equals BIL. That means we can write the maximum force as shown. This equation can be used only when the current and the magnetic field are at right angles to each other. If the wire is not perpendicular to the field, but is at some arbitrary angle, as in the figure, the magnitude of the magnetic force on the wire is given here. F equals BIL sine theta, where theta is the angle between B and the direction of the current. The direction of this force can be obtained by use of the right-hand rule number 1. In this case, you must place your fingers in the direction of the positive current I rather than the direction of V before curling them in the direction of B. The thumb then points in the direction of the force as before. The current naturally is made up of the charges moving at some velocity, so this really isn't a separate rule. In this figure, the direction of the magnetic force on the wire is out of the page. And if the current is either in the direction of the field or opposite the direction of the field, the magnetic force on the wire is 0. So we can still use the, let's see here. Oh, well, we won't mess with it. We'll talk about the right-hand rule in this type of situation in the future. Let's see. Most speakers in sound systems work by exploiting the magnetic force acting on a current carrying wire in a magnetic field. Take a look at this figure of a typical loudspeaker, which consists of a coil of wire called the voice coil, a flexible paper cone, and a permanent magnet. The coil of wire surrounding the north pole of the magnet is shaped so that the magnetic field lines are directed radially outward from the coil's axis. When an electric signal is sent to the coil, it produces a current in the coil. The magnetic force to the left acts on the coil. You can test this by applying right-hand rule number 1 to each turn of wire. When the current reverses direction, as it would for a current that varies sinusoidally, the magnetic force on the coil also reverses direction. And the cone, which is attached to the coil, accelerates to the right. An alternating current through the coil causes an alternating force on the coil, which results in vibrations of the cone. The vibrating cone creates sound waves as it pushes and pulls on the air in front of it. In this way, a 1 kilohertz electric signal is converted to a 1 kilohertz sound wave. Okay. The figure shows an electromagnetic pump. Artificial hearts require a pump to keep the blood flowing, and kidney dialysis machines also require a pump to assist the heart in pumping blood that is to be cleansed. Ordinary mechanical pumps create problems because they damage the blood cells as they move through the pump. The mechanism shown in the figure has demonstrated some promise in applications such as these. A magnetic field is established across the segment of the tube containing the blood flowing in the direction of the velocity v. An electric current passing through the fluid in the direction shown has a magnetic force acting on it in the direction of v. As you can see by applying the right-hand rule, this force helps to keep the blood in motion. Okay, this ends our this section on magnetic force on a current carrying conductor. The next section is 19.6 magnetic torques.